Almost all PCC is made by direct carbonation of hydrated lime, known as the milk of lime process. The milk of lime process is simple in concept. Mine high-purity calcium carbonate rock. Crush the rocks to the particle size needed for processing small stones or powder. Separate some of the impurities from the crushed rock. Calcium heat in a kiln to 1850 degrees Fahrenheit, which takes the calcium carbonate apart, forming lime, carbon oxide, and carbon dioxide gas. The carbon dioxide can be captured for use. Add the lime to water to form calcium hydroxide, hydrated lime or slake. Separate out additional impurities from the slake lime. Combine the captured carbon dioxide with the slake lime. Calcium carbonate reforms, and since it is insoluble in water, precipitates out. Separate additional impurities and grate from the PCC slurry. If the PCC is to be used in a paper mill or shipped to a latex paint plane, the lower solid slurry may be used as is or processed to bring up the solids level. Then test before transfer or shipment. If the PCC is to be used as a dry product, the slurry is dewatered, dried, milked, packaged, and test.
Tubular reactors are commonly used in the manufacturing of gasoline, oil cracking, the synthesis of ammonia from its constituents, and the oxidation of sulfur dioxide to sulfur trioxide. A tubular reactor is shown above, which is utilized in nitrogen compound oxidation studies. Tubular reactors are steady-state continuous flow devices that can be used to mix various chemicals. To complete chemicals reactions, the function of the reactant's position is used rather than the function of time. Tubular reactors often have 3 or more phases for distinct chemical processes. Tubular reactors that are single-phase and only handle one product at a time are also available. Solid-state phase. This phase comprises of immobilized biomass or biomass aggregates on various carrier materials. Phase liquid. A tubular reactor with a liquid phase made up of water, contaminants, nutrients, and other products is possible. Gaseous phase. This phase involves the operation and design of 2 separate phase systems, such as a liquid-solid phase. It is a more simpler phase that can be used for 2-phase reactions rather than 3-phase processes. It is also the most important phase for various gases, such as gas feed or air, which includes CO2.
The goal of this project is to provide a novel method for reducing reverse osmosis or OR concentrate flow while increasing recovery. A novel procedure is being developed to boost recovery value by using continuous crystallization of calcium carbonate at a constant supersaturation level provided by a continuous rise in retented TDS while the RO is in circulation mode. Through the use of crystallization, we can extract calcium carbonate from RO concentrate. This suggested solution make use of spiral wood membrane module with open channel that may handle water with significant scaling and fouling potential without any pre-treatment. The experimental approach is explained and experimental chart depicting precipitation kinetic are shown. The circulation mode of the test membrane unit was used and recovery value of 95% of greater were achieved. The RO concentrate was continually flowing through the precipitation reactor, which contained seed crystal. By infusing caustic solution into RO concentrate, seed crystal formation was started. The concentrate solution, which retained or rejected by salt and contaminants, is less than 1% of the initial input water volume and may be extracted as slurry moisture together with wet fluid.
This is the picture of tubular reactor. As you can see, a tubular reactor is composed by a tubes, shell, baffles, reformer, heating gas input, and heating gas output. For tubes, inside the tube walls, there were catalyst pellets. It used to preserve their mechanical rigidity. Next is shell. Shell is the outer layer of reactor and it acts as a wall, as well as its function is to protect the reactor. Next we have baffles. It promotes better flow of fluids for maximum efficiency. For reformer, it depends on the sector. It will rearrange molecular structure of hydrocarbon. Lastly, we have heating gas input and heating gas output. Heating gas input is where the gas enter, as well as the output is where the gas exit. Next, for laboratory scale SFTR, it is composed of a mixer, segmenter, bubble tube, and decanter. The mixer function is to mix mixtures to become a homogeneous mixture. Next, bubble tube will carrying out gas-liquid and gas-solid liquid reaction in a variety of important industrial reactions. Lastly, we have decanter. Decanter will separate solid materials from liquid in slurry. Some advantages of SFTR were as below. The first one is large conversion rates. The second one is low operation cost. Next is continuous operation. Lastly is perfect heat transfer. Next, SFTR also have some limitations, which were existence of thermal gradient, poor control of temperature, and expensive to maintain.